factorizable in terms of each of the separate physical systems. This is the part of this is the assumption of locality that actually gets violated by quantum mechanics. So there's loads of, what I'm trying to say is there's loads of sort of ambiguity and detail, how non-local it can behave, and there's been loads of subsequent investigations into that. So I'm going to try and set out some of the main results in the timeline. I'm going to try and start, so I'm going to try and do it all on the whiteboard. I'm going to try and do some categorical definitions as well to appeal to us all. So yeah, and then I'll try and move swiftly on from that. But yeah, hopefully you'll be able to see some of the underlying structure there, and hopefully it'll appeal to you to some degree, probably more than it actually appeals to me. Yeah, so just a touch more history before I go into it. So after the original result by Bell, the mathematical prediction that we can see non-local correlations at a distance between two quantum systems, there was obviously a massive experimental effort to try and reproduce this result in the flesh. And the earlier attempt, because it proves to be such a technologically demanding experiment, there was lots of skepticism surrounding it, of people kind of rejecting the mathematical structure and saying that there's no way that our universe behaves non-locally. There must be something wrong with the theory itself. So there was basically this sort of iterative sequence of events of experiments being proposed and then being carried out, but then being rejected, and being rejected on the basis of these so-called locality loopholes, right? Which are certain kind of caveats to a lot of the experiments which took place up until the 1982, I think, where there was the first like massively conclusive, very technologically demanding experiment took place to demonstrate the effect, and that won the Nobel Prize in 2022. So there's still a lot of interest in it. There's still a lot of exploration into how to exploit this example of quantum advantage. Okay, so yeah, to start with the sort of abstract definitions, and then I'll try and take it into the category of Hilbert spaces to have a look at how it manifests itself in the quantum world. So I'm going to start off with, am I all right over here with the camera? Yep. Great, great. So starting off with a monoidal category. So we get a unit I, the functor and two objects, and uniters, which the one I use, I'll call it lambda. A state of an object A isomorphism from the unit into that object. Excuse the rough writing here. I'm a bit sad actually that Connor's not here, because Connor was the one who persuaded me to do the whiteboard talk. So hopefully Connor's watching remotely, and hopefully there's some pride there. A joint state of A and B isomorphism from the unit into this object, because our object, because our functor is a monoidal functor. A joint state is a product state when we have the following commuting diagram. Is a product state when there exists start with the state S. So a joint state S is a product state when there exists S1, S2 also states such that, so here's our product state going from the unit into a tensor V. And if we apply the uniter here, one of the uniters, which is a natural isomorphism, right? So we apply it in the other direction, and we apply it at the unit itself, I, then we arrive at this object, and then we apply the morphism given rise to by these two independent states. So yeah, when we can write the state in this form, then it's a product state, and a joint state is not, when it's not a product state, it's an entangled state. So an entangled state is entangled when not a product state. Okay. So if we're in set, for example, and we endow it with the monoidal structure using the terminal object in set, the singleton set, then a state of a set is a morphism out of that singleton set into the set, so it's equivalently picking out one of the items of that, one of the elements of that set. A joint state is picking out an element of the product, the Cartesian product of those two sets, so it's picking out a pair of two sets. That'd be a joint state of two sets. And if we're in set and we have the categorical product and we are using the terminal object, then every joint state is a product state, right? Because it's a categorical product, right? So entangled states don't exist in the category of sets. So in the categorical formulation of quantum mechanics, the category of sets and functions is used to model classical classical determinism in physics. So yeah, nothing probabilistic about the physical systems that can be modeled with the category of sets in the physical context. However, quantum mechanics obviously takes place in Hilbert spaces, which are the vector spaces which have an inner product which is complete in a certain sense. It satisfies some completeness property. So if we station ourselves in the category of Hilbert spaces over the complex field, so we have complex vectors, we have objects which are complex vector spaces, morphisms are bounded linear maps, and we have this complete inner product in each of the spaces. Okay, yeah. So firstly, we have to endow it with the monoidal structure. So we define the functor via a universal property, which is that given two Hilbert spaces U and V, I do apologize about the writing. Oh, good. I'm glad. I'm trying to, huh? Oh, good. I've been practicing a little bit, you know. It's much worse in the meetings with Fred, anyway. So Fred will be glad to see that I've improved. Yeah, so we've got two Hilbert spaces in. So yeah, given two Hilbert spaces, I'm going to try and define this functor using the following universal property that given two such vectors, and so we're applying the Cartesian products on the underlying sets. So we've got an element from each of these vector spaces. We've got a vector from each. So the functor comes equipped with this bilinear function f, function, not map, not bounded linear map even. So here's f, which is bilinear. So that takes us into this joint Hilbert space, such that for any other Hilbert space W and bilinear, well, that's good. See, that's a better response than I got when I read about this. Yes, yes, but then we get this. Yeah. Which is linear, right? So then this is a map in the category, right? But then, yeah, this is just bilinear, right? Well, yeah, it kind of, yeah, because it kind of encodes some. It's kind of encoding that this behaves bilinearly, right? I guess is the intuition. This functor, huh? If it's finite dimensional, it's bounded. Yeah. 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 Is that true? Right, I see. Yeah, I see. Yeah. Oh, okay. So yeah, the question is that um, for Hilbert space, so it should work for vector spaces, but for Hilbert spaces, um, the only requirement that G is bilinear doesn't necessarily give us a map in the category of Hilbert spaces because it doesn't seem to imply that this is a bounded map. I don't know. I'll have a look at that. Yeah. I've not read about that. So there must be something in this. It must be. It must be. It must be. It must be right because this isn't my work, right? So yeah. No, no, it's interesting though. This. This. Oh, we're not in Hill. We're not in Hill. This is a Cartesian product. Yeah. So yeah. So the diagram's in set. Yeah. Yes. Yeah. We're obtaining a map in Hill. Yeah. 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 There must be. Or maybe. Yeah. Right. Yeah. I see. Yeah. I don't know. Yeah. I'll have a look. I'll have a look. No. It's interesting though. It's interesting. Yeah, I wanted to provoke some debate with this because I was also looking at it and it's not so straightforward for me to kind of grasp. But um, I've been harassing Fred about this diagram for weeks. Say again. Um, so, sorry. Say again. Sorry. No. It's fine. Sorry. Sorry. Yeah. Sorry. Yeah. It comes equipped with this with F. Yeah. But it's not linear. Yeah. Yeah. Okay. Okay. So then, if we fix G accordingly, then we can extend this to morphisms, right? So um, we can uniquely extend this functor to morphisms in the following way. So given say nu1 and nu2, we can obtain nu1 tensor nu2 on u tensor b as nu1. Right, um, and similarly, we can obtain the uniters, the associator. Yeah, so and then we can see how these look in this category. How the states look in the category. So in a Hilbert space. Oh, sorry, did I forget to say the unit? So yeah, we fix the unit. Um, we fix the unit to be the one-dimensional Hilbert space, right, which is exactly the set of complex numbers. And yeah, so that's our monoidal unit. What's a state in this category? It's a morphism out. So it's a bounded linear map out of the complex numbers and into the Hilbert space. Which is equivalent to exactly picking out a single vector in that given Hilbert space, right? Because we can form an orthonormal basis in this Hilbert space just with the single number 1, right? So because every linear map is defined exactly by its action on a basis, the information encoded by a state is exactly just a single vector in a state of a given vector of a given Hilbert space is exactly just a single element of that Hilbert space, right? Because we only have to consider its action on the number one, on the complex number one, because the number one makes up an orthonormal basis for this vector space. And yeah, so a product state is one that is it then emerges to be a separable vector in terms of the tensor product. So it can be written as at the topmost tensor product, right, of two vectors. Yeah, it can be written as a topmost tensor product in the joint Hilbert space, and an entangled one can't be written as a topmost tensor product, right? You can't separate it into one vector tensor another, right? Like, so if we are okay, so I'll give an example. So in Dirac notation, which I'm not sure how familiar people are with this, but just to put it simply, we use that to denote a. I don't think I even need to go into that. So yeah, if I've got a vector in U tensor V, then this is a product state when there exists J1, J2. That looks like an S, doesn't it? Dear me. See, I started writing J's in a nice way, and then it just got worse and worse. It started to look more and more like an S. What you need to do is what you need to do is just top from graph. Okay. Or you can complete the loop as well. I see. Right. Yeah. Okay. We'll talk about that as well. We'll have a long technical discussion about this as well. So yeah, all I'm saying is that this state can be written as oh god, I'm gonna go really simple with it. J1 tensor J2. So all I'm saying is that these two J's exist. Yeah. I think you were saying top level. Yeah, that's what I meant. Yeah. Maybe that's a phrase that I've just picked up myself. Yeah, I've invented that phrase. Maybe topmost, top level. Yeah, top level. Right. Yeah, and if we can't express it like this, then it's entangled. And yeah, so the existence of an entangled state ever since like the very early formulations of quantum mechanics have had to deal with these joint entangled states. It's unavoidable to deal with this phenomenon, and this is what led to the kind of unhappiness with the formalization that you can't separate the two states, right? So there's somehow the two states are somehow interlinked and connected, even when at arbitrary distance, right? So the physical implications in the real world were disturbing by this mathematical structure, right? Which is what led Einstein to his criticism and led to the whole hoo-ha in the 20th century. Okay, good. Great. What do you mean? They're vectors, right? They're vectors. Yeah. Um, they're like they're superposition. They can be superpositions of they're quantum states. They're but it's like yeah. So a qubit, for example, is the quantum generalization of a bit, and you, in the and so a qubit q lives in c squared. So it's it consists of a pair of complex numbers, and the idea is that that sort of models this superposition of this kind of superposition of the two possible states rather than it clearly being one state or clearly being the other, like a classical bit. We model like this kind of superposition or uncertainty. It's like the kind of no, but I also didn't make this clear enough, so it's a fair question. 100%. No, it's a pair. Because the basis is there's two it's two-dimensional. It's a two-dimensional Hilbert space. Yes. Exactly. No problem. No, it's fine. It's fine. No, because it is confusing, right? Because there's two components to a complex number, right? So I see where it arises. It's also been a long time since I did this. So yeah. Okay, so now let's look at the manifestation of non-locality. The um, the first kind of concrete manifestation of Bell's theorem, which is it's called the CHSH game or the CHSH experiment. It's from the early 70s. So John Stuart Bell published his original paper suggesting that non-local correlations can be exhibited by distant qubits. But the first experimental plan and the most sort of intuitively realizable manifestation is called the CHSH game. So that's this scenario here. So we start with this source, a source of particles or classical bits, and it distributes this information to, there we go, to these two distant measurement apparatus, right, which conventionally called Alice and Bob. And let me think. Do you know? I know someone called Bob though. Yeah. We could do a physical demonstration. Yeah. Yeah. No problem. Cool. So yeah, yeah, but they're not necessarily separable. So Alice and Bob each receive an input bit, which are called X and Y, and they output then a bit A and B. So X, Y, A, B, all are bits. Yes, classical bits. So we then ask the question, how should these, so if we allow for probabilistic behavior here, so we want to talk about the probability that Alice outputs A, Bob outputs B, um, given 2-bit inputs X and Y. So yeah, given values of A, B, X, and Y, what's the probability of that eventuality? I'm just going to neaten that a bit because I might have to write a bit more than this. So Einstein's requirement of local causality, that is influence can only travel at most the speed of light, requires that if Alice and Bob are simultaneously performing their measurements, that Bob shouldn't be able to change his choice of measurement. So if X and Y are corresponding to which measurement Alice and Bob perform on the particle they receive, right? So Bob shouldn't be able to change his choice of measurement and that to influence Alice's measurement result. That's our local causality requirement. That's our relativistic requirement. So mathematically speaking, if so, this is the no signaling requirement. So yeah, if we sum over Bob's outputs, so this should be always equal to, so yeah, this is just, this is Y prime, yeah. I also have the same problem with the letter Y. Yeah, so this represents that Bob's changing his choice of measurement, right? And the probability should remain the same. And then we want the same for Alice changing her measurement choice, right? So I could write it out again symmetrically. Sorry, and this is for, yeah, I've got to say this is for all A, X, Y, Y prime, right? Key thing there. um, so yeah, so that's our requirement for no signaling, and yeah, this is Einstein's requirement. What's our requirement called? So there's another requirement that we can ask for called local realism, right? Which is that these the probabilistic behavior at each measurement site should be mathematically separable, right? That's how we model independence in probability, right? So this is called local realism. Maybe, yeah. Yeah, yeah, yeah. Yeah, 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 yeah. Well, yeah, yeah, yeah. So like this is the thing. So like in the popular literature, it kind of gets made out to be violating no signaling. It's just like you can communicate non-locally, right? But you actually can't. You can only violate local realism. So it's only distant they're non-locally correlated, but they're actually not in violation of Einstein's requirements at all. So there's a really interesting relationship there, right? It kind of reveals a little bit about the relationship between quantum mechanics and relativity, which is obviously a huge problem in foundational physics, unifying those two things, the relationship between those two things. So it seems that either quantum particles should be able to behave more non-locally than mathematics lets on, or Einstein hasn't actually asked enough about locality in relativity, right? Um, yeah. So yeah, our requirement for local realism then. So we denote the joint state. So denoting the joint state by lambda. Sorry, I actually use that for the uniter, so maybe I'll call it mu. And then we want to allow for any kind of randomness at the source as well. So this is going to be our kind of locality preserving state of the bits that are being received by Alice and Bob, right? So this, classically speaking, actually corresponds to a mapping from the input measurement to the output, right? That's classical behavior, yeah. It's fully deterministic. It's a determinist. This is exactly a mapping from Alice's input to her output and Bob's input to his output. But we can allow for some randomness. So I'm going to call so uppercase gamma is now, this is a probability distribution over these locality preserving hidden states being distributed by the source. So this, so intuitively, right, we'd say that the probability of output A, output B, given inputs X and Y, we should be able to write it like this. So we sum over the probability distribution. Yeah, so we're saying that there exists some deterministic mapping like this, and there exists a probability distribution over it. And then we denote, this is how, so then we include the probabilistic separability like this. So the probability of Alice outputting A given her measurement, her input X, and the mapping mu multiplied by the probability of Bob's kind of, these are called the local marginal distributions. Okay, so this is just to encode the separability of the states, right? Sorry, of the behavior of Alice and Bob. So we allow for probabilistic behavior, but it should all be explainable via a local mapping, right? So Einstein's criticism was that although quantum mechanics looks as though it's predicting non-local effects, there should be some sort of hidden aspect of the quantum system, some hidden variable that describes. So there's some hidden characteristic of particles which allows them to appear as though they're behaving non-locally when they're in fact not. But this is as far as locality goes, right? This is our requirement of locality. So this is a cheers, thank you. This is an intuitive requirement, right? So if you ask anyone, then I think everyone would agree with this requirement, right? Yeah, 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 yeah. A little survey. Yeah, yeah, yeah. Exactly, right. Yeah, yeah, yeah. Being generated at the source and then distributed, right? Yeah. Yeah, so it's locality preserving. And yeah, so then we can, so returning back to our entangled states, if we're in, if we're in C2 and I'm going to define this vector here using Dirac notation, which we just use this kind of form to denote a vector. And this is one of the so-called Bell states. There's 4 of them, and they're called maximally entangled states, right? And so we have a normalization constant, and then because we're in C squared, we have 2 basis vectors, right? So we're talking about qubits here. So our basis vectors are denoted by 0 and 1. So this is our 0 basis. This is one of the Bell states, right? This is the maximally entangled state. This is the most entangled state because there's a way of quantifying it, how entangled a state can be, by just like including 2 proportionality constants and then mixing it with unentangled white noise. Then you can actually measure entanglement, and this is the maximally entangled one. Yeah, yeah. Yeah, 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 right. Exactly. But to Alice and Bob, they they look like they're performing their measurements, but they look like they're just getting a even probability for either outcome, right? Yeah, yeah, yeah. And so you don't know what Bob received, but he received the same thing, the same outcome, but you can't communicate to Bob. To each of the parties, it looks like they are getting a random measurement result. But then when they communicate afterwards, then their outcome always matches, or their outcome's always opposite. Yeah, yeah, that's so it is locality. It's local causality preserving, right? It preserves the no signaling. It's not signaling. So quite a jumbled response, but basically, if Alice and Bob receive this joint entangled state, and then Alice and Bob perform measurements, depending on their input bits X and Y, they observe correlations which are in violation of this requirement. So just very quickly, because I know I'm running out of time. Okay, great. Yes, yes, but I'll try and finish in time for the hour. So yeah, there's our no signaling requirement. I think, sorry, yeah, I'll take away the no signaling requirement. So we're just left with local realism now. So just looking at local realism. Yeah, yeah, it's satisfied. Yeah, 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 yeah. And this is the quantum strategy it's called, right? So from this, there's not too bad a derivation. So you can derive a bound on this set of probabilities using this requirement. So first defining these terms called the correlators. As so these are called the Alice and Bob's correlators. Um, so you can derive this so-called Bell inequality, right, which is the restriction on the distant correlations imposed by the requirement of local realism. That's called a Bell inequality. And in this scenario, our Bell inequality is that. Whoops, sorry, I meant to rewrite it in terms of the correlators. yeah, so we can, this is our local bound, right? So we've got, these correlation terms, which are defined like this, you can derive a local bound on them starting from here. And when you expand this out, it ultimately, it becomes, just bear with me here, when you expand out this sum and the correlators, the coefficients here become -1 to the power of a plus b plus xy. So maximalizing the left-hand side of our Bell inequality requires that this is even, right? But a nice way of expressing it is that, so the common way of expressing it is that a addition modulo 2b is equal to x times y. So for this reason, this is called the CHSH gain, because it's like Alice and Bob are receiving these inputs x and y, and they're trying to output a and b such that the modulo 2 addition of those two bits is exactly equal to the product of their two input bits. So it's kind of by the by, but I just wanted to give you a bit of a taste of how this so-called Bell test works. It's like they're playing a game, right? We start with this requirement of local realism. We get a bound on the sum of the correlators. The coefficients end up like this. So maximalizing this left-hand side becomes playing this game, right? And we can set up Alice and Bob's measurement options, their measurement operators at each measurement site, such that for if Bob receives y is 0, he performs a certain quantum measurement. If Bob receives y is 1, he performs a different one. And then all in all, we get that's how we get this violation of this inequality, right? And that's how we violate local realism in this scenario, right? So does that make sense? Does that make sense? I'm making it. Yeah. 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 So yeah, like they can. Yeah. 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 Yes, they can. Yeah. 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 Exactly. So yeah. Yeah, so they can devise a deterministic mapping between them and then spatially separate themselves. So they can devise a strategy like if we receive 1, then we'll output if we receive 1, we'll output 0. So they can try and find the best way to satisfy this in the majority of cases. But there's 4 possible cases, right? Sorry, there's 16 possible. There's 4 possible scenarios that they receive via x and y, and they can inherently only deterministically satisfy 3 of them with any deterministic strategy. So they can devise any mapping between themselves before they spatially separate, and they can only satisfy 3 of the 4 cases of x and y, right? But quantum mechanically speaking, they can, for any combination of x and y, they can yeah, 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 exactly. Yeah, exactly. Yeah. Um, yes. Well, yeah. But yeah, as they repeat, as if you repeat it, yeah, you get yeah, it's all probabilistic, but the overall probabilities are non-local. But yeah, so what I did mention before was the so-called locality loopholes that lots of skeptics proposed about this sort of Bell test. One of them was that because these are literal physical measurement apparatus, the experimentalists originally were planning we're saying, okay, let's fix Alice's measurement to be this bit, and let's fix Bob's measurement to be this bit, and then we distribute the entangled photons or entangled electrons or whatever, and perform the measurements. But the sort of skeptical point of view of that was that this information is now known in the universe and has had. So, however, this information of what Alice's measurement operation is going to be, and what Bob's measurement operation is going to be, that information can spread to the source and can spread to each other because it's been predetermined just for the sake of experimental convenience. So the one that won the Nobel Prize for one of the three guys, so then there was lots of experiments afterwards, but the one in 1982, they released the photons and then randomly picked Alice and Bob's measurement inputs after the photons were released. So they had to really quickly choose their perform kind of, alter their measurement choice while those photons were traveling towards the measurement apparatus. So it's a massively technologically challenging thing, but to kind of close this opportunity for skepticism surrounding it. I think something like a kilometer or kilometer and a half. So it is really, really quick. It's really, really quick. Yeah, well, then it's. I think maybe they did it on a mountaintop, maybe on mountaintops or. No, it must have been in a tunnel. It must have been in some sort of vacuum because the purity of this entangled state is going to be constantly interfering with its surroundings. Yeah. There's no way they can just shine light. Yeah. I should have checked that. I should have checked this, but yeah. But it's interesting how they do it. But yeah, right. That's all. Yeah. I hope I managed to convey the significance of that to you. But yeah, it is, isn't it? Interesting. Yeah, that's cool. Very cool. Very cool. Yeah. Yeah. That's very cool. That's very cool. It reminds me actually, our upper bound here in the quantum scenario is 2√2, and I think if I remember correctly, our no signaling bound is actually 4, right? So Alice and Bob can win this game every time if they're obeying the no signaling requirement. Yeah. 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 Yeah, yeah. Yeah, and in sets in the category of relations, you get in the entangled states of like the square subsets. So you take two sets and you set of all square subsets are entangled states in category of relations. So yeah, there's loads of really interesting manifestations of that. Yeah. Oh, sorry, they're the product states. You're right. Yeah. And the entangled, but they exist. There exist entangled states. Right? Right. Cool. Yeah. Is that just is that a relation just with the probability assigned to each potential mapping? So it's like a, so, right. Yeah, yeah, yeah. Yeah. I think um, so. There's another really interesting. So you've probably heard of quantum teleportation, right? Do you know about how the teleportation protocol? Do you know about that? Yeah, 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 yeah. But there's like you can potentially relay correlations, right? So there's another sort of bell test like this where we have Alice, Bob, and Charlie, and two sources like this. And Bob is actually performing a measurement in the Bell basis. So his eigenstates of his measurement here are actually entangling measurements on the two joint states here. So Alice and Charlie end up with entanglement, even though they never shared a particle from the same source originally, which is like even more scary, right? Yeah. Yeah, yeah, yeah. Yeah, it gets destroyed. It gets destroyed afterwards. No signaling. Yeah. Yeah, yeah, yeah. But there are some uses of it, but I'm more wanting to present it from the foundational standpoint. This was the standpoint that I studied it from as well. Yeah, exactly. Yeah, 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 yeah. Yeah, 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 exactly. Yeah. Yeah, 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 exactly. Right. I mean, yeah. It initiates some sort of collapse of the wave function. Yeah. Yeah, yeah. Any because an observation collapses it destroys information in a sense. An observation, sorry, it collapses the waveform, the wave function. Yeah. That's an interesting point now, yeah. 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 Yeah, yeah, yeah. Yeah. Yeah, yeah, yeah. There has been a bit of work on that. I've not really got that far. This is kind of yeah. I've done some of the reading, but not all of it. So I'm not fully sure what the sort of categorical formulation, if there's any sort of categorical idea behind it. So. Yeah, 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 yeah. I've just not got around to reading it all yet, unfortunately. But I'm interested to read more on it. Yeah, yeah. Cool. Cheers, guys. Thank you. Do we not get one from Fiona because Fiona's was